Okay, so let's get into one of the weirdest and deadliest disasters in American history. It's an event that honestly sounds kind of funny at first, but once you understand the terrifying science behind it all, well, it becomes a story about corporate greed, ignored warnings, and the deadly physics of something you probably have in your pantry right now.
So, picture this. It's January 15th, 1919, in Boston's North End. And for January, it's a surprisingly warm day. Then, out of nowhere, a gigantic storage tank just explodes. It unleashes what one reporter famously called a delicious brown tsunami. We're talking more than 2 million gallons of raw molasses flooding the streets in this thick, destructive wave.
Now here's where the story just gets unbelievable. This wasn't some slow, lazy spill, no. This wave of molasses was a violent, raging wall of syrup, estimated to be moving at an incredible 35 miles per hour. That is fast enough to literally rip buildings off their foundations and just sweep everything away. And that leads us to the central mystery here, right? We all know molasses. It's that super thick, slow-pouring stuff. So how in the world could it move with that kind of terrifying speed? Well, the answer is a perfect storm of really bad decisions and some pretty basic physics.
You know, the craziest part is that this disaster wasn't a total surprise. Not at all. That tank was a ticking time bomb, and a lot of people knew it. The warning signs had been there for years, but they were just ignored, fatally ignored.
Let's just walk through how this whole thing built up. So the tank gets rushed into service back in 1915, made with pretty shoddy steel. A year later, it's already leaking. And the company's brilliant solution? They just painted it brown to hide the molasses streams. Seriously. For the next couple of years, people living nearby kept complaining about these weird groaning and rumbling sounds coming from it. And then, the final straw, a huge shipment of warm molasses gets pumped in just days before it all came crashing down.
I mean, just look at this list of failures. The steel plates? Way too thin. The riveting? Terrible. And this is the real kicker. They never even did basic safety testing. They never even filled it with water to check for leaks, which was standard practice even back then. Every single warning sign, from the actual physical leaks to the sounds of the tank literally crying out under stress, was just brushed aside.
So, okay. The stage was set. The tank was a complete disaster waiting to happen. But to understand the pure violence of that failure, we've got to look at the science. This is where the story goes from just being about negligence to being a straight-up physics lesson.
So the first big idea we need to get our heads around is viscosity. It's just a fancy word for a fluid's thickness, right? How much it resists flowing. So something with high viscosity, like honey or cold molasses, it moves super slowly. And something with low viscosity, like water, flows really fast and easy. This is so important for what happens next. And right here, this is the absolute game changer, temperature. When molasses is cold, its viscosity is off the charts. It barely moves. But when you warm it up, its viscosity plummets, and it can flow way faster. And remember, the disaster happened on an unusually warm day, and that last batch of molasses they pumped in was also warm. Okay, now let's throw pressure into this chaotic mix. You've got 2.3 million gallons of molasses. That's about 26 million pounds of liquid, all crammed into this 50-foot-tall tank. Just the weight of all that goo created this enormous outward force. It's called hydrostatic pressure, pushing on the walls, especially at the bottom of the tank, right where the steel was already failing. So you can see how all these pieces create a recipe for absolute catastrophe. You start with the shoddy tank. Then, that warm day causes the molasses to expand, which ramps up the pressure. But wait, there's more. The molasses was also fermenting, which produces carbon dioxide gas, adding even more pressure from the inside. All those forces combined were just too much, and that brittle steel didn't just leak, it failed, instantly and completely. And that gets us to the answer to our big question. What happens to all of that incredible, pent-up energy from the pressure? The second that tank failed, all of that energy had to go somewhere. It was instantly converted into kinetic energy, the energy of motion. The molasses wasn't just spilling out, it was launched like a cannonball, creating that deadly high-speed wave. The aftermath was just horrifying. But it also forced the kind of reckoning that led to some really important changes in engineering and public safety. And believe it or not, there are lessons from this sticky mess that are still super relevant today. And let's not forget the very real, tragic human cost of all this. 21 people died. Firefighters, children, just regular people. Another 150 were seriously hurt. It was a horrific event that left a scar on that community for generations. So when you look back at the whole thing, you can see it wasn't just one mistake. It was a total system failure. You had engineering arrogance, this belief that cutting corners was good enough. You had economic pressure to get it done fast. You had a stunning ignorance of the basic science at play. And it was all allowed to happen because there were basically no regulations, no real safety standards to stop it.
In the end, the Boston Molasses Flood is this powerful, if, well, sticky, reminder of a very simple truth. Ignoring basic science isn't just a mistake. It can be absolutely fatal.
And that kind of leaves us with one last thing to think about. I mean, this happened over 100 years ago, but that core lesson feels pretty timeless, doesn't it? What happens when we decide that speed and profit are more important than sound science and safety? It really makes you wonder, what warnings are we just painting over today?